All right. Can you all hear me? Yeah, okay. All right. All right. Does anyone have any questions before we get started? Cool. All right. Since we had so many asynchronous videos last week, I wanted to start with actually some practice problems before we roll into the chapter 4 cycloalkane content. Might just have to be after page 1. I don't know why it won't let me move. There it goes. Nope, whatever. Doesn't matter. Okay. Yeah, that's probably enough stuff. All right. Go ahead and try to name that molecule. Are we still working on number 1? Okay. I'll give you 1 more minute to finish number 1, then we'll talk about that. Then I'll give you a couple more minutes to do 2 and 3. All right. If you didn't get 2 and 3 down, don't worry. I'll still give you some more time. Just we're going to do number 1 first to make sure that we're all on the right path. All right, so to get started, we need to find our longest carbon backbone, the longest carbon continuous chain or continuous chain of carbons. So when I look at this, if I go left to right, I can get 1, 2, 3, 4, 5, 6, 7, or I could come up and get 7. The thing that probably will make life easier is if you can recognize your primary functional groups right away. So I see that I have this carboxylic acid. I know the carboxylic acid is highest in the priority chain. It is tops. That means the carboxylic acid will always be number 1 because you need to give your primary functional group the smallest number possible. So it probably would be easier to start counting from there. So I know that carboxylic acid has to be 1, so then I can find my longest carbon chain going out from that. And that's how I get my 7. Whoops. So starting out, we need to identify our backbone. Our backbone is made up of the root and our parent functional group. What is my root? What do you use for 7 carbons? Hept, good. That is your root. So your root is that meth, eth, prop, but, pent, hex, hept, oct, non, dec. You need to know those 10 in that order. Our parent functional group is going to be what? Alkane, alkene, alkyne. Alkane. So we're going to take that A and E because we have all single bonds between those 7 carbons. So essentially, we lack a parent functional group, so we use alkane as our suffix. So our backbone is that heptane. Next is going to be easiest if we identify all of our functional groups. We kind of jumped the gun and already figured out that the carboxylic acid is going to be our primary. But for review, let's do all of them. So this one, I already told you, is the carboxylic acid. So what is the suffix that it would get? What do you use to designate a carboxylic acid? Yeah, oic acid, thank you. So we're going to use oic acid for the carboxylic acid. It's going to go on the very end to indicate to us that we have a carboxylic acid in our molecule. All right. Then I see this one carbon chain. What is that called? Methyl, good. The meth is for the one carbon. The ol is because it's a substituent. So this is a methyl group. What functional group is this? Alcohol, good. What do I use as the prefix? Hydroxy, excellent. If it was the primary, what would you use? What's your suffix if alcohol is the primary? Ol, that OL, good. You just take the end of it. It's just OL. But we're going to take secondary because remember, you can only have one primary. And we already know the carboxylic acid is going to be the highest. So that means I'm going to take the secondary, the prefix for the alcohol. All right, what functional group is this? Ketone, good. I know because it's the carbonyl, the carbon-oxygen double bond with carbon on either side. So that is my ketone. Bless you. If it's a secondary functional group, what do we use? What prefix? Oxo, good. If it's a primary, then what do we use? Own, yeah. You just take the end of it. Own. And again, we can only have one primary, so we're taking that oxo for the ketone. What functional group is this? Aldehyde. And in the video, I actually don't remember if I actually said this, so I'm going to explain this now. With the aldehyde, I told you there were two optional prefixes, right? Does anyone remember what they were, if it was a secondary? So formyl and oxo, good. What do you use if it's the primary? Al, AL. So it's weird because you take the beginning of that one as your ending, but whatever. All right. So the difference between the formyl and the oxo is that oxo just means double bond to oxygen. That's what it's telling us. Formyl means specifically that you have a carbon, oxygen, and hydrogen. That's what formyl tells you. It tells you have those three atoms as a substituent. So the fact that I am including carbon 7 in my backbone tells me that I have to use oxo here. If I wanted to use formyl, I could not include carbon 7 in my backbone because formyl means this whole thing. So we'll name it in both possible ways, using both formyl and oxo. But right now, we got to use oxo if we're including carbon 7. All right, so then we already know our locations because the carboxylic acid had to be number 1. So then our methyl is 2, our alcohol is 3, our ketone is 5, and then our oxo is 7. Then how do I assemble all of my prefixes? Alphabetical order. The number stays with the thing that it's describing the location of. So we're going to compare our methyl M, H hydroxy, and O of oxo. So what comes first alphabetically? H, the hydroxy. So that gives me 3 hydroxy. right? What comes next? The methyl. So then I get a dash, because you always have dashes between your letters and your numbers. Dash 2-methyl. What am I going to do with my oxos? Group them together. Yeah, so we get that 5, 7, because you always have a comma to separate your numbers from each other. And then it becomes a dioxo. The di tells me that I have 2 of them. I have 2 carbon-oxygen double bonds, is what it's telling me. I still do it alphabetically off the O of oxo, not the D of di. So that gives me the 5,7 dioxo. Then I get my heptane because I have just letters next to each other. I don't need another dash. So it just becomes heptane. And then because the English language struggles to do those double vowels, the EO sound, we're going to drop the E and just write oic acid. So that molecule is 3-hydroxy 2-methyl 5,7-dioxoheptanoic acid. If I wanted to name this using formal, if I wanted to use that formal prefix, that changes my backbone to BC6. And then my formal is coming off of carbon 6. So using that, I need more space. I would now get A, B, C, D, E, F. Yeah, F comes first. 6 formal, 3-hydroxy, M is still next, 2-methyl, 5-oxo, for the ketone, ketones are always oxo, hexanoic acid. So the difference becomes that, if I use formal, that includes the carbon. So the carbon can't be double counted. I can't include it in both the backbone and the substituent naming. So if I'm using formal, that takes the carbon out of the backbone and into the substituent. If you count the carbon in the backbone, then you have to use oxo. And both of them are totally correct. You can use either one. IUPAC has slight preferences on when you use one over the other. They're really pedantic. So I'm cool with either one. So you can either use formal or oxo, but you have to use them correctly. So you'll frequently see that on my answer keys, I will include both answers as acceptable answers. All right. Are there any questions about that naming process or the name in general? Yes. That's a great question. So the carboxylic acid, you don't have to specify because it always has to be carbon 1. So because it has to be that carbon 1, then you're just going to put it, you can have 1s be assumed. So, and actually that's true of always. 1s can always be assumed. 1s can usually be assumed. There are a couple of exceptions. The exceptions become if you have like 2 carboxylic acids, then you have to, 1's on one end, 1's on the other. You need to say like 1,7 dioic acid, like to say that there are 2 carboxylic acids. Then you'd have to include the 1 if there are multiple functional groups that are being grouped together. And then you should also include the 1 when you're doing the branch naming convention. So if it's like a substituent of a substituent, then you'd put a 1 inside those parentheses. But otherwise, 1s can usually be assumed. Yes? Yes, to know if it's going to be primary or secondary, there actually is no tertiary. It's just primary, and then everything else becomes secondary. And it's in that where you get the list of what is your prefix and suffix, it's that order. That is listed in order, where the top is highest priority, the bottom is lowest priority. So whatever's at the top of that list becomes the primary, and then everything below it becomes a secondary. So you only take whatever suffix is highest up on the list. Yeah. Yes. You have to memorize the order of that list. So a trick to help memorize it is that there are two things. One, it is based on oxidation state, which I like to think of it as it's grouped by number of bonds to heteroatoms. So my carboxylic acid has 3 bonds to a heteroatom, more bonds to heteroatoms, higher up, whereas my aldehyde only has 2 bonds to the oxygen, ketone has only 2 bonds to oxygen, alcohol has only 1 bond to the heteroatom to the oxygen. So that means that my carboxylic acid is going to be highest. Then I would get aldehyde and ketone would be next. If the carboxylic acid didn't exist, then one of those would become my primary. Then alcohol is lower on the list. So higher up is more bonds to heteroatoms, lower down is less bonds to heteroatoms. Then when you're looking at it, if you can be a terminal functional group, meaning you're on the end and like you're basically forced to be carbon number 1, then you're high in priority. So that means that your aldehyde is going to be higher than your ketone because your aldehyde is on the end. Like there's no carbon on either side. There's just a hydrogen, so that ends the carbon chain. So if it ends the carbon chain, it's going to be higher up. So like a carboxylic acid is higher than an ester because your ester has a carbon chain that continues on both sides. So the ester is lower down than the carboxylic acid because the carboxylic acid doesn't have carbon on both sides. So first is the number of bonds to heteroatoms. Then next is if it's on the end, then it's higher than a functional group that's in the middle. Any other questions? Okay. Then go ahead and try the next 2 problems. Whenever you're ready, go ahead and also just check with people around you to see how your answers are matching up. All right, let's go ahead and regroup. Hopefully you got something. If not, we'll talk about the process, and then you just want to make sure you're doing more practice. So you want to practice, this is the level of exam style questions you can expect. So you want to make sure that this is the quality that you're, or like the level of difficulty that you're up to before you get to the exam. All right, so when we're drawing from a name, I find it easiest to first interpret what each of the aspects of the name mean. And it's usually easiest to go right to left. So what does that own tell me? I have a ketone. And what does the 2 tell me? On carbon 2, good. What does the En tell me? The double bond, the carbon-carbon double bond, it's an alkene. What does the 3 tell me? It's on carbon 3, so it'll be between carbon 3 and carbon 4. What does the but tell me? 4 carbons are in my backbone. So this is my backbone. This is my primary functional group. This is going to be my secondary functional group / substituent. All right? What does the YL tell me? Substituent. So that's how I knew it's separated there, was I saw that YL and that was my dividing line. What does the hex tell me? 6 carbons. What does cyclo tell me? It's a ring. So I'm going to have a ring of 6 carbons as a substituent. I'm going to have a 6 carbon chain hanging off of my backbone. Where is it located? Carbon 4. What does the trans tell me? Yeah, it means opposite sides for your primary or your higher priority groups on the alkene. So it means the alkene has the high priority on opposite sides. So I usually would just write the word opposite, but to clarify, the alkene has high priority on opposite sides. That's what the trans tells me. All right, so now to draw it out, I find it easiest to start with the backbone and then put everything on it where it needs to be. So my but 3-ene, that's going to be my backbone. So start with the 4 carbons. This is your molecule. You're drawing it. You get to pick which direction you number in. I usually default to left to right because that's what I prefer. I usually read left to right, but you can do right to left. Totally correct. It is your molecule. So I'm going to do left to right, and I'm going to just number it so that I know where I need to put everything. So that now takes care of the but part. My alkene is between carbons 3 and 4. So that means I need to put my double bond there, between 3 and 4. That takes care of my alkene. My ketone is on carbon 2. So I get a double bond oxygen on carbon 2. Next, I get the 6-membered ring coming off of carbon 4. This is usually where students make a mistake and they try to make that carbon in the ring carbon 4. That's not it. The backbone is here. Cyclohexyl means I need 6 carbons as my substituent. I need to have a total of 10 carbons in my molecule. So I need to have, off of carbon 4, I get the 6 carbon ring. That takes care of my cyclohexyl off of carbon 4. And I already made it trans because I made my groups on opposite sides. If I needed cis, usually what I would do is then erase that and just flip it over and put it up here. That would be cis because then they'd be on the same side when you draw a line through the carbons. When you connect the carbons, if they're on the same side, it's cis, opposite sides, it's trans. Cool? All right. Any questions about that one? Yes? I'm so glad you asked that question. Okay, so the ring is going to be your backbone when you don't have a primary functional group. Primary functional groups are always going to be higher in priority than any hydrocarbon. So it's always going to be that they are going to take higher priority. The second I get that suffix, that is going to say, all right, that has to have the lowest number possible. That determined that had to be my true backbone. This 4-carbon chain would have to be the backbone because that has the primary functional group. If there was no primary functional group, then the ring would be my backbone, regardless of the size of it. Yes, that's a really good point of distinction. Yes? Yeah, so for trans, what we're looking at is you go atom by atom, the higher the atomic number, the higher the priority. So I'm looking at the left side of my alkene first. You do left side and then right side, or just pick one side. So I'm comparing the two elements that are directly connected to the alkenes. What are the two elements directly connected to the alkene? Carbon and hydrogen. So I have a carbon and an implicit hydrogen. Which one has the higher atomic number? Carbon. So that tells me right away, I don't even have to keep going. I just know that side's high priority and that side is low priority because the hydrogen would be low in priority. You go atom by atom until you find a difference. So then I go to the right-hand side. And now on the right-hand side, what are the two elements directly connected to that carbon? Carbon and hydrogen. Which one's higher? Carbon. So that means that now this is high priority. The whole chain becomes high priority. That side is low priority. So when I connect the dots, when I draw a line through the carbons of the alkene, I look to see are my high priorities on the same side or opposite sides. For trans, I want opposite sides, so that is the trans alkene. Cool. Do we have any other questions about this one? Did you have a question? Stretching, my bad. Okay, all right, this last one. There are two ways of going about this. You could either just name it directly, or you can convert it into a line diagram first and then name that. Personally, I find that easier, especially starting out, I think it's easier to go from the Newman. I meant to ask you that. This is the Newman projection. And we're gonna go from the Newman to the line diagram. So I'm going to fold this over. I can either fold it over to the right or I can fold it over to the left. It doesn't matter which way I rotate it, as long as you end up with the, like you're paying attention to where it goes. So I, by default, will rotate it to the right, just that way I'm always consistent, but you can do it either way. I just try to be consistent, that way I know that I'm like, yeah, I'm doing this correctly because I always do it this way. But you need to be able to do it both ways. So when I look at this, I look at the in-plane lines, the ones that are straight up and down, and I draw those first. The methyl is down, so that is down here. The hydrogen is up, so that's there. This is that staggered conformation, so that methyl is down from the relative perspective. I'm assuming that my eyeball is here. I'm standing here. So the methyl goes straight down, the hydrogen went straight up off the back carbon. Because remember, the front carbon is the dot, the circle is the back carbon. So off the front carbon, I get an alcohol and 2 hydrogens. So off this front carbon, Oh, I shouldn't have an alcohol. What did I do? I lied to you. That is my front carbon. I really hope that didn't just mess anybody up. So this is my front carbon. Let's just start over. So I knew I drew the eyeball on the wrong side. So far, we're still right. Like our process, like what we're drawing is right. I just drew my person on the wrong side. So I know that this is my front carbon. So that hydrogen that went straight up had to be closer to me. So that's why I was drawn on the wrong side originally, right? I am on the right-hand side of this molecule. I'm essentially taking this molecule, which is stacked like this, and just folding it over. Taking it like this, rotating it over. So when I do that, I take this and I fold it over. That's going to make this alcohol be a wedge. And then the other hydrogen would be a dash. Because when I fold this over, so this chain comes out like this, right? It's actually stacked. When I fold this over, this alcohol is going to pull out like that and point towards you. So it starts here, and I fold it over. If I'd gone the other way, where it starts like this, and I fold it out, then my alcohol would be on the dash, right? That's all I'm doing is I'm taking it, and I'm folding it either to the right, or I fold it over to the left, right? You just got to be consistent with whichever way you go. So I'm taking it and I fold it over to the right. That's why my hydrogen was up on the right. My methyl, which is down, is now down on the left. So this alcohol got bent out and is now a wedge pointing out at you. This hydrogen, when this folds in, that hydrogen now gets pushed into the plane. Does that help with wedges and dashes, imagining it that way? Okay, some people, good. The nice thing about the back carbon is that we have two ethyls, so one's a wedge, one's a dash. But I can also know that the one that's on the same side as the alcohol in the Newman projection is on the same side as the alcohol in the line diagram. So I know that this ethyl is that ethyl because it's on the same side as the alcohol in the Newman. So it also would have been folded out towards you. All right. Next, I need to expand my ethyls. Why do I need to expand my ethyl? So we can see where the longest carbon chain is. Because right now, it looks like the carbon chain is only 2 carbons long with 3 substituents. But I could potentially highlight in to either one of those. So I need to figure out, all right, well, which way do I need to go down? I got to go down the longest carbon chain. So if I make this now just a normal line diagram, it would look like that because ethyl is 2 carbons. So I need to have 2 carbons, the edge of that wedge, and then the end of that line. That's 2. 2 carbons for the other ethyl that's on the dash is the end of the dash, and then the end of the line. Those are 2 carbons. Methyl is 1 carbon, so it's just the end of the line. So now when I go to try to find my longest carbon backbone, always start by your primary functional group. The alcohol is the only functional group on this molecule. Remember, alkanes are not functional groups. They are the default to be an organic molecule. Alkanes are not functional groups. So you start by the alcohol, your primary functional group, and then you're going to count out. If I go left, I get to 2. So this is 1, 1, 2. And then I'm like, all right, if I go down, that is 3. That would be a 3-carbon chain. If I go up the wedge, that gets me 3, 4. That's longer than 3, so automatically I know methyl isn't my longest carbon backbone. It's going to be through one of the ethyls. Then if I go 1, 2, I can do 3, 4. Is there a difference between the ethyls? No, so it doesn't matter which one you pick. You can pick either one. So I'm going to just make it 3, 4. So that means that my backbone is how many carbons? 4. So what is my root? Bute. What is my parent functional group? Alkane, because it's all single bonds between my backbone. What suffix do I use for my primary functional group? All for the alcohol. And again, the 1 can be assumed. Then I get a methyl, which it already said was on, but now it's on carbon 2. And I get an ethyl on carbon 2. So now I get to assemble my pieces. I need to put it in alphabetical order. So that ethyl comes before the methyl. So this is going to be a 2-ethyl, 2-methyl, butan, all. I'm also okay if you want to write the E in, if you write ANEOL, that's fine. That's more of like a grammatical thing. So like, you're still indicating to me that you know what the parent functional group and what the primary functional groups are, so I'm cool with that. So on an exam and a quiz, I accept both spellings, with or without the E. So if you just want to like by default always put the E, that's fine. If you want to put the 1, I would also accept that. So if you want to be really explicit, to be 2-ethyl, 2-methyl, butan, or we'll say butane 1 all, I'm cool if you put the E in the 1. Right. I'm not okay if you drop off the N. You will never lose the N. That's a part of what makes it the parent functional group, is the AN, EN, or YN. You need to have that N. Otherwise, it's not clear. Reason why it's not clear is because, especially for our 5, 6, 7, and 8, they become penta, hexa, hepta. We just normally drop the A because you don't do the double vowels. But it technically, if you had like a diene, so like, for example, this molecule is cyclopentadiene. The A comes back because now I have a vowel and a consonant. Cool. All right. Any questions about that? All right. Do we have any questions at all? Yes. Mm-hmm. Yeah, so when we're looking at the Newman projection, when you're in the staggered conformation, staggered will always be lower than eclipsed. So when you have these like spokes on the wheel, that's always going to be lower in energy than this conformation. So if I rotated this, to make it HET, ET, H, OHMe. So if I rotated this, now it's in the eclipsed conformation because these bonds are now on top of each other. That's always going to be higher in energy than staggered. Within your eclipsed, the total eclipsed is higher than just normal eclipsed. So this would be just a normal eclipsed because ethyl is bigger than methyl and alcohol is bigger than a hydrogen. So that means that my big groups are my alcohol and my ethyl. So if they were on top of each other, then it would be considered totally eclipsed. That would be highest energy. The biggest things as close together as possible, highest energy. Then within our staggered conformation, we have the Gauss interactions, and that's going to be between two non-hydrogens. So my Gauss interactions here are just those two. My anti-conformation, I don't really have one here, but it essentially is that, because this is where I get the lowest. My higher staggered conformation would be if I have the two ethyls next to the alcohol. So that's kind of anti. You don't normally use anti unless it's like clear that all the big groups are totally opposite each other. But yeah, anti just means the largest groups are 180 degrees. Cool. Any other questions? Yeah. Say that again? Yes, the hydrogens on carbon 1 get assumed to be there because alcohol will only have one bond to carbon. That's absolutely right. So then we know that those hydrogens get accounted for because of that. When we say the butane, that's what's telling us how many hydrogens have to be attached to the carbon. Yeah, that's good. Did you have a question as well? So so if you're looking at an energy diagram and you actually have the relative energies and you're calculating it, you could still get it adding to 0. Is that true? And still be anti? Yes, you could have it not add to 0 and still be anti. So you really just want to identify, like go front carbon, back carbon, find the biggest thing on each. So the front carbon, the biggest thing is the alcohol. Back carbon, biggest thing is the ethyl. And you want them 180 degrees from each other. So, which this is also ethyl, that's the alcohol. Cool. All right, any other questions about Newman projections? Okay, so what we're starting is our cycloalkanes. So we're gonna do naming our cycloalkanes and our bicyclic alkanes. Then we'll get into our stereochemistry. We'll do ring strain, looking at three-dimensional structures, and cyclohexane is gonna be the bulk of it. This is where we're gonna spend most of our time this week, is looking at our chair conformations and how to draw them and the relative energies of them. When we're naming, because this is review, because we're already talking about naming, the cycloalkanes, they're going to be a form of unsaturation. So they have 2 fewer hydrogens than the straight chain. So remember that unsaturation are pi bonds and rings. That is going to take away 2 hydrogens to become a ring. In our nomenclature, if you are just a hydrocarbon, all you have are carbons and hydrogens, I don't have a primary functional group, the ring is going to be your parent. If you have multiple rings, the larger ring is your parent. And we'll do fused rings next time. All right, have a wonderful day.